Today we're going to stick with our section multiplication and division of whole numbers, and we're going to move into the division part of this. Last time we looked at some models for multiplication as well as properties of multiplication, and we're going to go on to the division section and look at some of those same kind of things this time. All right, so to start with, definition of division. Much like when we did subtraction, it's defined in terms of the other operation. So division of whole numbers says that for any whole numbers a and b, where b is not 0, if a is divided by b, it was going to equal c, if and only if c is the unique whole number such that b times c equals a. Okay, and once again, like, this is how kids learn division. Hopefully, they have their multiplication facts down, right? They know that 2 times 3 is 6. They know that 7 times 8 is 56. And then you turn it around on them and you say, okay, then what is 56 divided by 8? And because they know that 8 times 7 is 56, they can do that backwards. That's what it is. So A is actually called the dividend, B is called the divisor, and the result of the division is called the quotient. So there's a little bit of vocabulary, most of which you've seen, but it might not have been recent. All right, there are four different models for division. 2 of them are actually titled the same, and your book does not differentiate. But I want to show you both versions or varieties of it. And in particular, the reason I want to show you that is because when you take proportional and statistical reasoning, one of them shows up, and it's not the one that the book originally mentions. And so it's a useful fact later on. So our first model division is called the set partition model. So we've got Junie, and Junie has 24 rocks, and she wants to give them to 6 of her friends. How many rocks will each friend get? So we have 6 friends, and literally what you would do if you were in Junie's case, right, and you didn't know how to do division, you'd probably have your 6 friends there, and you'd make piles, or you'd have the people there, right, and you'd give them 1 rock each. And then you give them another rock each, and you keep going until all the rocks are gone, right? And if it was evenly divisible, everybody would have the same number of rocks at the end. So in terms of drawing a picture of this, we would end up having these sort of groups, and each group would have, in this case, 4 rocks. So I have 1 group, 2 groups. Oh, that wasn't what I wanted to do. Try one more time. There's 4 groups. All right, I have my 6 groups of rocks, okay, and I didn't draw them in the same way I described them, but you heard what I said, which was that they would each get 1, they would each get a second one until you've used up all your rocks. And when you're all said and done, you'd have 6 friends with how many rocks each? 4 rocks. Okay, so in this scenario, you know how many groups you are dividing the objects into. This is the example that does not work very well when you start dividing things by fractional amounts. Because somewhere along the way, and it is in our proportional statistical reasoning class, you do something like 6 divided by 1/2. How do I make half of a group? Right? Like, this is 6 groups. Okay, fine. So 24 divided by 6, I make 6 groups. But if I do 24 divided by half, how do I make half of a group? It doesn't make contextual sense. But if you do it like this, it does. So this is, again, the set partition model. It's a variation of it. Junie has 24 rocks. She bags them in groups of 6. There's not 6 groups. There's groups of 6. And if she gives 1 back to each friend, how many friends will receive the rocks? So what we're actually able to determine this time is how many objects we're giving to the friends, whereas in the other example, we're determining how many friends get our objects. Okay? They're equivalent, but this one actually works for division by fractions. Let me finish this problem, and then I'll talk a little bit more about why that makes sense. Okay, so here are my 2 of my groups of 6. And here are my other 2 groups of 6. And what I end up having then, of course, is there are how many groups of 6? Well, there's 1, 2, 3, 4. So 4 friends get my rocks. Okay, so let me go back to my 6 divided by 1/2 example. When I have 6 objects and I make them in groups of size 1/2, I can do that. Let me just give you an object that we can split up so that it makes sense. How about McAllister's cookies? Big giant things, right? You guys been to McAllister's, you've seen them, they're like this big. If you were to split 6 giant McAllister's cookies up into groups of size 1/2, how many 1/2 size cookies would you have? 12. That makes sense, right? I can make groups that are a certain size 1/2, but making half a group, which is the other version of this, doesn't make sense. All right? So I'm not asking that you, I mean, when we create these here, you'll see in examples, but you know, they're just variations. They both have the same name, but they are doing something slightly different. All right, let's take a look at a couple more. Missing factor model. In a missing factor model, we actually have the same question as we had earlier. Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? So in the missing factor model, it has to do with how you actually write the solution out. So I have, 24, and it's supposed to be divided by something, and I'm supposed to receive 6 friends or give them to 6 friends. So in terms of a missing factor model, it means that 6 times something is equal to the 24. So we're trying to find this missing factor that makes that work. And that would be, of course, the number 4. And in this case, that would be 4 rocks. Okay. Last example is a repeated subtraction model. Repeated subtraction gets people a little bit confused. It is definitely not efficient. So efficient means quick, okay? But it's easy. It's just not efficient. So same question, 24 rocks, give them to 6 of her friends. How many rocks will each friend get? So going back to how I described that the actual process of this would work is that you have the 6 friends. Imagine them standing there in front of you and you going down the line and they all get a rock. And then you go down the line and they all get another rock, right? And we keep repeating this process until the rocks are gone. Well, every time you do that, you have 6 fewer rocks than you had before. So each time you are repeatedly subtracting the same value. So what is 24 minus 6? 18. And then I do it again. What is 18 minus 6? 12. And then what is 12 minus 6? 6. And then what is 6 minus 6? 0. And then the answer is simply how many times did I do this? How many times did I go down the line? How many times did I subtract 6? And the answer is 4, right? It's 4. 4 times, 4 rocks, I guess, in our context. I get 4 rocks. So a note here. 3 of these 4 models above do not represent different types of word problems. That's what happened when we did multiplication and subtraction and addition. They all represented different types of problems. But instead, they represent different ways of solving a problem. All right? So in your groups, this is your next thing you're going to do, this is why you're in groups, is you're going to create word problems and solve them with each of the 4 models. Note, 3 of your 4 problems will be the same. So what you're really going to do is you're really going to create these 2 variations of each other. One where you're doing something to divide it up and you're determining the size of the groups, and the other one where you're determining and dividing it up and determining how many groups there are. So like in class here today, I did one of these operations. Did I determine how many groups I had, or did I determine how many people are in each group? Do you know what I did? I was focusing on how many people are in each group. That's what I was focusing on. So I was trying to figure out how many people I had so that I didn't make my groups too big. I don't want groups that are bigger than 3. That's the way I do my groups. So I wanted to make sure that I had the right number to divide you into, right? Divided by 7 is what we did, so that my groups were small. Okay? So we divided by 7 because we have a group not here. That's why. The 2 people that are not here, they were 7s, in case you were curious, because nobody said 7. Okay, so go ahead and turn your desk, chat with your people. You're creating 2 word problems. That's what you're really doing. One where you determine how many objects are in the set. One here where you are determining how many sets you have. All right, so we had some examples you guys created. So I want every group to be willing to share one of them. And the rest of the class as a whole is going to try to decide which of the 2 categories it fits in. Is it the group that fits in, I know how many people are in the group, so to speak, right? Or is it the category where I know how many groups there are? Those are the 2 different categories. So we're going to try and decide that together. So I think we're going to start on my left-hand side. So let's start with this group right here. Share either one of them that you have, doesn't matter which one, and we're going to, as a class, see what we can come up with. Okay, read one for us.
Sam has 18 cookies. She has 6 friends that she wants to share them with. How many cookies does each friend get?
Okay, so do we know the group number or how many are in the group? Like how many groups we have or how many are in each group? How many groups we have? We have the 6 friends, right? Yeah, absolutely. All right, next group.
Becky has 32 cupcakes. She puts them in baggies of 2 to give to her friends. How many friends will get cupcakes from Becky?
Okay, so which one do we know in this case? How many are in each group? Are you guys 2 groups here or 3? 2 groups. Alicia, or you're over here. Gotcha. I was all turned around. Okay, Alicia and of this group right here in the middle then. Somebody read one of them.
Katie makes 10 cookies and wants to share them with 5 friends. How many cookies will each friend get?
Okay, so what is it we know in this case? The number of groups, right? 5 friends, we have 5 groups. Yep. Up here at the front.
He said Bob has 18 cookies. He bags them into groups of 6. If he gives one back to each friend, how many friends will get a bag of cookies?
Cool. And so which one do we know here on this? The size of the group, right? We know the size of the group. Very good. All right, so we'll just move straight back. Throw through the middle here. Emily, are you in this group or are you guys split sideways?
Oh, yeah, I think so.
The 3 of you? Okay, so what do you guys have?
Which one?
Either one of them. Just pick one.
Yeah, okay, I'll read one.
It's okay.
Kate has 15 cupcakes. She wants to give them to 5 friends. How many cupcakes will each friend get?
Okay, so what do we know? Yeah, the number of groups, right? We have 5 friends that we're splitting them into. All right, and last group at the back. What do you guys have?
The pet store, groups 18 bunnies and groups of 5. How many owners are there for each group?
Okay, so we know the number in each group on this one, right? Because you have 9 in each group. Very good. I think yours might have been the only non-food example. Did y'all notice that? I did. I started with that. It was probably my fault. All right, let's shift gears just a little bit and talk about properties then. We did this with subtraction and multiplication and addition as well. But with subtraction in particular, we approached it from this perspective, trying to decide which of these properties hold for division. Okay, so again, closure seems to catch us all the time. But closure means if I take 2 numbers in the set and I operate on them, in this case with division, do I end up with a number in the set? So if I take 2 whole numbers and I divide them, will I always end up with a whole number? No, I will not. Can you give me an example? Right. 5 divided by 2 is not a whole number. Right? 2 whole numbers divided do not give me a whole number solution. This would be one, though, that's... Could we come up with lots of examples where they do end up with whole numbers? Absolutely, we definitely could, but that's not what it means, right? How about commutative property? Commutative property means the order of things, right? So if I switch the order of division, will I end up with the same value? No. And an example for that, I can use your 5 and your 2, you just did. So 5 divided by 2 does not equal 2 divided by 5, right? No, it doesn't work. The associative property, it doesn't work either. This one's a little bit trickier to see examples. So I have ones I've got written down here. So for an example, if I do 12 divided by 4 divided by 2. So what is 12 divided by 4? 3. And 3 divided by 2, by 2 would be 1.5, right? But let's do it in the other order. What happens when I do 12 divided by 4 divided by 2? So what's 4 divided by 2? 2. And then what's 12 divided by 2? It's a question mark, yeah. We're about to change it anyways. 12 divided by 2 is 6, right? So these are not equal. 1.5 does not equal 6. Everybody really wants there to be identity properties for division. Because it is true that if I divide by 1, I don't change the numbers, right? Sure. 7 divided by 1, 7. Do you remember the other part of the identity property that would fail? You have to be able to flip it. So this one doesn't work because anytime I flip it, so like A divided by 1 is going to equal A. But typically speaking, 1 divided by A does not. I mean, it would work if A is 1, but that's the only time it would work. Flipping the order doesn't make it work. We had a 0 property for multiplication. The 0 property for multiplication said that if you multiplied by 0 on the left or the right, you get back 0. So is there a 0 property for division? No. If you divide 0 by something, it works, right? 0 divided by a number is 0. But what happens when you try to divide by 0? Do you guys remember? It is undefined. And let me show you exactly why it's undefined. Do you remember how we defined division? We started with something that looked like this. A divided by B is equal to C. And we said this is only true if A is equal to B times C, right? So let's take that A and that 0 here for a minute so you can see why it fails. If I do A divided by 0 and it equals C, I'm similarly asking what number times C is going to get me back to A, right? 0 times C. Well, that's never going to get me back to A, right? There's no number I can multiply by 0 and achieve anything but 0. And that's why that doesn't work. So the distributive property, what do you think? No, we're on a no track, right? It's definitely not going to work. So let me show you again an example. If I had 20 plus 10 and I divide by 5, this would actually, the question is, would this work if I distributed, right? So 20 divided by 5 and 10 divided by 5. Okay, so what is 20 plus 10? 30. And 30 divided by 5 would give me 6. What's 20 divided by 5? 4. And 10 divided by 5? 2. So does it work on this? It does here. But as with every property, there's more than one direction to test things, right? So what if I actually had 20 divided by 10 divided by 5? And I'm testing the order in the other direction. Well, the question is, does this equal 20 divided by 10 plus 20 divided by 5? Okay, well 10 divided by 5 is 5, right? In the parentheses. And what is 20 divided by 5? It's 4. On the right-hand side, what's 20 divided by 10? 2. And what's 20 divided by 5? 4. 4 does not equal 6, right? This one didn't work. So it didn't work in both directions. All right, one last example for today. It's a real quick one. This is one of those like student work kind of examples, and what do you say as a teacher kind of deal. JJ claims that the following is true because the distributive law, where A and B are whole numbers. 3 times AB is equal to 3A times 3B. How would you help him?
Can you go back a little bit?
Oh, sorry.
Yeah, how did you get 4? Okay.
On which one?
The very last one. 20 divided by 10 divided by 5. You said it's 4.
Did I write it wrong? Over here?
Narrative.
It was supposed to be 10, wasn't it?
Okay.
Sorry. It was moving too quickly. My bad. Thanks for catching it. I don't even know if I had it in my notes. Oh, I just don't have it written down in my notes at all. I just have it not equal in my notes. Yeah, it's 10. Because it should have been a 2 here and 20. So 20 divided by 2 is 10. But they're not equal, right?
Right.
They're still not equal. Yeah, you're right. Okay, take a look at JJ. What is JJ misunderstanding?
I'm supposed to like answer that one.
Yeah, sure.
Just to add them together.
Okay, so he is misunderstanding what distribution operates, right? Or how distribution operates. Distribution is a property that involves multiplication and addition, or multiplication and subtraction. And he's using it, it says all multiplication here, right? So in particular, in multiplication, we have associative and commutative properties that allow us to move things around, right, and restructure things. So right here, actually, let me do it on the other side. Right here, I could literally rewrite the right-hand side from what he thinks is equal, like this, right? That's associative and commutative happening simultaneously. And then you can see that the 9AB certainly doesn't make sense that that's 3AB. So if we're working with him, we would want to help him understand that distribution is a combination of 2 operations. But all he has here is 1 operation, just the operation of multiplication. And within just the ultimate operation of multiplication, that's not distribution. Does that make sense? If you were wanting to show him how it worked without using properties like I did, you could also choose values for A and B. You know, let A equal 1 and B equal 2, and show him that his equation doesn't hold. The values are different when you plug those numbers in on both sides. And it's not just one example. You could come up with lots of examples that would not work, too.